Hello everyone, my name is Antoine and I'll talk to you about the discovery of the top quark. Before talking about the experiment, I will just give you a little bit of historical context. So in 1973, Kobayashi and Maskawa predicted the existence of a third generation of quarks to explain the observed CP violation in kaon decay. Then in 1977, the bottom quark was discovered. This convinced physicists even more to believe that there had to be another quark. They knew it would be heavier than the bottom, but they weren't sure by how much. You may ask yourself, why do we care about a particle so heavy it practically decays instantaneously? Well, not only are we curious as physicists, but the top's mass would also help to put a constraint on the Higgs boson mass. The joke in the meme is that the top quark is too short-lived to be in a hadronic state. Its half-life is on the order of 10 to the minus 25 seconds. Let's talk about the discovery. In 1995, there were two simultaneous publications from Fermilab announcing the discovery of the top quark. One from the CDF collaboration and one from the D0 collaboration. Both are named after the detectors they work with. The two detectors are placed along the tevatron, which accelerate proton and antiproton up to an energy of 1 TeV. For your information, it was shut down in 2011. It took 18 years to observe the top quark after the discovery of the bottom quark because of their mass difference. Creating a top quark is something that requires a lot of energy. In this video, I will focus more on the D0 experiment. This is an image of what a detector looked like. They were measuring the energy of the particles using calorimeters, and they provided a better energy measurement for the hadrons than the CDF detector. The trajectory of each particle was also measured. D0 only detected charged particle and it did not measure their momenta, except for the muons. I will quickly define what jets are as it will be relevant later. At high energy collision, the quarks can escape from where they are confined, creating a quark-antiquark pair. You can have a quark or a gluon with a net color charge, so they must combine to form colorless hadrons. These hadrons line up with the direction of the original quarks. Now let's talk about what the experimentalists searched for. They created top-anti-top pair and looked at the decay chain where one or two of the W boson decayed into leptons. Now let's start from the beginning. A proton and antiproton collide together like shown here and it creates a top-anti-top pair. Then the top decays into a bottom quark and a W boson. The bottom quark will emit a jet. The W boson can either decay into a quark-antiquark pair or into the leptons. It's important to know that for the antitop, we just need to change all particles into antiparticles. Also, the image on the right is to show the possible ways to create the top-antitop pairs. Now let's have a look at the results from the D0 collaboration. So they calculated that if the top quark did not exist, they should see 3.8 plus or minus 0.6 events. But in reality, they saw 17 events. So this leads to a standard deviation of 4.6 sigma. In more details, the column in green are when the two W bosons decay leptonically. The orange columns are when only one of them decay into leptons and the other decay into a quark-antiquark pair. The blue column looks at the B-tagged event. A B-tagged event is when a muon, that is the result of the bottom quark decay, is observed. Now let's have a look at the results from the CDF experiment. When they looked at the one lepton event, they used two methods called SVX and SLT. The difference between the two are that they look for different particles during the decay process of the bottom quark. They chose 37 events from the two methods. They also looked at a case where both W decayed into leptons, and from that they saw 6 events. So this leads to a standard deviation of 4.8 sigma. As both experiments were very close to 5 sigma, they both announced their discovery at the same time. Both experiments also measured the mass of the top quark. They looked at events where only one of the W decayed into leptons. To measure the mass, they performed a kinematic fit on the 4 jets with the highest energy and they looked at all possible permutation, but they made sure that a muon-tagged jet was assigned to a bottom quark. They calculated the chi-squared of each jet assignment and only kept it if the chi-square was less than 7. Finally, they did a weighted mass average using the chi-square. For the D0 collaboration, it gave them a mass of 119 GeV with a pretty big uncertainty. So this is the figure that appeared in their original paper. The first graph, they used the orange and blue column of the table I showed you earlier to do their fit. For the second graph, they removed the constraint that there had to be a minimum energy to be considered an event. This is because they wanted more points for their fit. They got 27 points, while in part A we only have 14 points. The CDF experiment also used the same method and they reported a mass of 176 GeV, which is much closer to the modern value of 172.52. They also had much smaller uncertainties. The top quark is still used in today's research. Due to its high mass, it interacts a lot with the Higgs boson, which is ideal when you want to probe for new physics. Alright, so this is the story behind the discovery of the top quark. Thank you for your time and I hope you appreciated it.